I already prepared 3 lectures, yeah, so basically 3 hours. So possibly I will skip some of the part, yeah, probably the one in Ramsey numbers. So I will just show you how we use Hadamard matrices to find bounds for Ramsey numbers. Yeah, I will not go into details. Yeah, but the first 2 parts will be about labeling. The first one is about distance magic. The second one is about anti-magic labeling. Yeah. So this is what I planned originally. So this is the definition of distance magic labeling that I have shown you on 2 days ago, right? So remember, what we add is the labels of the vertices adjacent to one vertex, right? So we label the vertices, and then in each vertex we add the label of all adjacent vertices, right? Yeah. Okay, so I have shown you these examples. So what about the magic constant of distance magic graph? Yeah, so if we have a distance magic labeling with magic constant k, what happened to it? So of course, this is an easy observation that the magic constant has to be at least n, right? Yeah, why? Because there is a vertex which has label n. Yeah, and of course, if we so probably this is not really correct. So if we consider connected graphs, yeah. So if we consider connected graphs, so that vertex with label n will be adjacent to another vertex, right? Yeah, and then of course it will be the magic constant of that vertex will be at least n. Yeah. Okay. So here, if we also consider the disconnected graphs, yeah. So the magic constant will be n if and only if the graph is either P3, yeah, so path of 3 vertices, or P3 plus copies of C4. So this is the only graphs which has minimum magic constant. Yeah. Okay. So because this is the minimum one, so we have to go one by one, yeah, to see which one is achievable or not, right? So for n plus 1, this is the only graphs, yeah. So copies of C4, yeah, those are the only graphs. And for n plus 2, actually there is no graphs with magic constant n plus 2. Yeah, so we couldn't find any distance magic graph with magic constant n plus 2. Yeah, but for the other values, as long as it is odd numbers, yeah, we can. There is a construction. Yeah, so it was constructed in this paper by Professor Aromugam, Kamachi, and Kofar. The construction for distance magic graph with odd magic constant, for any odd magic constant greater than 3, greater or equal to 3, right? So it is already constructed, but for even integer, even magic constant, it is still open. Yeah. So this is one problem that you can work on actually. Yeah. So try to find construction of distance magic graph where the magic constant is even number. Yeah. So this is one of the problem. Okay. And so usually if we work with some definition, we want to try to find forbidden subgraphs, yeah, in the structure of the graph, right? Yeah. But in the case of distance magic graph, we couldn't find any forbidden subgraphs. Yeah. Why is that? Because it's already proved here that every graph is a subgraph of distance magic graph. So this is not really difficult. You remember that 2 days ago, we already showed that we can have complete multipartite graphs, right? Distance magic complete multipartite graphs, yeah. So you remember the magic rectangles thing, yeah. Of course, there is a condition yeah, for the number of vertices, the number of partition, yeah. But then we can arrange, yeah, so if we take arbitrary graph, yeah, we can arrange for the graphs, for that particular graph to be a subgraph of a multipartite graph, yeah. So yeah, you can think how to do it, but it's not really difficult. So from that observation, we can say that every graph is a subgraph of a distance magic graph, yeah. And some condition can be further restricted, yeah. So we can also have that every graph now is not just a subgraph, but an induced subgraph of a regular distance magic graph. So in this case, we still use the complete multipartite graphs, yeah, that we use in here, but we can arrange such that the graph under consideration is an induced subgraph, yeah. So this is a further a restricted condition, yeah. We can say that every graph is an induced subgraph of an Eulerian distance magic graph, yeah, with the same chromatic number with the subgraph, yeah. So we are from all of this result, we can say basically that there is no forbidden subgraph characterization for distance magic graph. So it is not that obvious, yeah, to decide whether a graph is distance magic or not, yeah. But actually, yeah, if we try to find all the distance magic graphs, we can, yeah, just small with a small number of vertices, right? We can find that they are very rare, yeah. So there are not many distance magic graphs, yeah. So for instance, so we already compute, we made a catalog of distance magic graph up to 9 vertices. So you can see here, for 8 vertices, for example, we have 120,000 some 12, yeah, 12,000 something graphs, yeah, non-isomorphic graphs. But from all these graphs, only 6 of them are distance magic, yeah. So, and you can see in the 9 vertices graph, yeah, so this is the graph with 9 vertices. There are a lot of them, yeah, more than 200,000 graph, but only again 6 of them are distance magic. So they're quite rare. They're very rare, actually, yeah. So these are the distance magic graphs of order 8, yeah. There are 6 of them. One is disconnected, yeah. You can see this is the graphs with the magic constant is this vertex, yeah. The adjacent vertices are this one, right? So 9, yeah. And this vertex again 9, yeah. So the magic constant is 9, yeah. And here the number of vertices is n, right? So this is actually the graph with magic constant n plus 1, yeah. That was already mentioned before, yeah, in the result of Gina, yeah. So, and this is the only family of graph which has magic constant n plus 1, yeah. So the others you can see, yeah, this is very trivial, yeah. The magic constant is 0, yeah, because they don't have any neighbors, right? Okay, so this is the all the distance magic graphs of order 8, yeah. And we also have all the distance magic graphs of order 9, yeah. And yeah, because they are quite rare, very rare, yeah. So some people try to generalize the definition, yeah. So why? Because we want to find more of them, yeah. So, but okay, so we generalize in the way that we don't only count the adjacent vertices, but we can also count vertices of particular distance, yeah. So if we talk about adjacent vertices, they are vertices with distance 1 from our point of view, right? So from a particular vertex, we see vertices of distance 1, yeah. Here, we can use any distance. Yeah. So if d is the diameter of the graph, yeah, and we can find the set of all distances. Yeah. So all distances will be 0, 1 to up to d. Yeah. And we can take any subset of that distance set. Yeah. Okay. So now we can define a new labeling, which we call the D-magic labeling. So this was introduced by Alan O'Neill and Peter Slater in 2011. Yeah. So again, this is a bijection. So we label only vertices. Yeah. And then we count the weight for the vertices with distance in here. Yeah. So here you can see that we have what we call the D neighborhood set. Yeah. So this is the D neighborhood set. What is this? This is just all the vertices where the distance between from X to the vertex here is inside this set D. Yeah. Okay. So this is called the D-magic labeling. Yeah. So similar to what we have before, but now we consider other distances. Yeah. So with this definition, yeah, our previous distance magic labeling is just the D magic labeling where D is equal to 1. Yeah, because distance magic labeling, we only consider the neighbors. Yeah, distance. Yeah. Okay. And there is also one magic labeling that has been defined, introduced in 2009 by Bina, and it is called closed distance magic. Yeah, closed distance magic. So basically, what he did is he counted the label of the vertex itself and also the neighbors. Yeah, so distance 0 and distance 1. Yeah, yeah. It can be. It can be. So if we include 0 in the D, then of course we include the vertex itself, yeah, because the only vertex with distance 0 is itself, right? Yeah. So like in here, when we say 0, 1, yeah, we also add the label of the vertex itself plus the labels of all the adjacent vertices. Yeah, but the D can be anything. It can be 0, 1, 2. It can be only 2. It can be 3. It can be 4. It can be anything. Yeah, as long as it doesn't pass the diameter of the graph. Okay. Yeah. So when this notion was defined, yeah, automatically we can ask two questions. Yeah. The first one, what about the magic constant of a particular graph? Yeah, so if we have a graph, yeah, if we are given a graph, is the magic constant unique or not? Yeah, I know some of you already work with edge magic total labeling or vertex magic total labeling. Yeah, you know that the magic constant is not unique, right? There is a range for the magic constant. Yeah, and you can have many labelings with different magic constant. Yeah. But so it is asked here, yeah, whether it's also happen when we consider D magic labeling, yeah, is it also happen the same way as in the edge magic total or vertex magic total, yeah. And the second question, yeah, because remember when we consider the distance magic, so only distance 1, they are very rare, yeah. From 200,000 graphs, we can only find 6. They are so rare, yeah. So now the question is, if we enlarge the distance set, can we say that all graphs has labeling for particular D, right? So we ask the second question: does there always exist a non-empty distance set D? Yeah, which is not everything. Yeah, of course, if we take the distance set is all the possible distance, yeah, 0, 1, 2, up to the diameter. If we take that distance, we just add everything. Yeah, of course, it's gonna be magic. Yeah, that's very trivial. Yeah, so, that's trivial. But now we want to see a proper subset, yeah, where the D-magic labeling happens, yeah. So okay, so both of these questions actually have been answered, yeah, and I will show you how we answer. Okay, the first question. It is actually surprising that the magic constant is unique. Yeah, because like the people who work in this area were originally working in the H magic total, vertex magic total, and we are used to the fact that the magic constants are there. There can be many of them. Yeah, we have a range of magic constant, and sometimes we can find all labelings with all the possible magic constants. Sometimes we cannot, but we are used to that. But here, the magic constant is actually unique. Yeah. Okay, so how to show this? The main tool of this is the adjacency matrix of a graph. Yeah, that's for the distance magic. But for the D magic, we use the distance matrix of the graph. Yeah. So here, O'Neill and Slater define what they call the neighborhood fractional dominating function. Yeah. So what is this? Yeah, this is a function from the set of vertices. Yeah, to this is the interval. Yeah, from 0 up to 1. Yeah, close interval. Yeah, so these are real numbers here. Yeah, and it is called the fractional dominating function if we add all the vertices, all. So this is supposed to be U, okay. So there is a mistake here. This is supposed to be U, If we add the map, the map of this function G for all the vertices U inside the D neighborhood, then it's always greater or equal than 1, Okay, so of course, if we use the function all vertices get 1, 1, 1, 1, this of course will be fulfilled, So that's if we set G to be 1, for all vertices, then it is a fractional dominating function, right? Because then in every for every vertex, we just have to count like how many neighbors, D neighbors, the vertex. Okay, but we want to minimize, we want to minimize. So overall of the fractional dominating function, we want to minimize the sum, the sum. We want to minimize the sum. Okay. So of course you can imagine if I use just 1, 1, 1, 1, we can still find probably we can find a function with less sum. Okay. So so this is the main theorem. So the theorem that says that the magic constant is unique. So this was proved by O'Neill and Slater in 2013, and it was also proved separately in the same year by Arumugam, Kamachi, and Vijayakumar. It was published in 2 different papers. The proofs are completely different. The one that I will show you is the one from Arumugam, Kamachi, and Vijayakumar. So if a graph is D-magic, then the magic constant is unique and we can count them. It is equal to n times n plus 1 over 2. So this is basically the sum from 1 up to n, right? Divided by this number here, which is the fractional domination number. So the minimum over like all the fractional dominating functions. Okay, so I just want to show you the proof by Arumugam and friends. So here, as I mentioned before, we use the distance matrix of G. So what is a distance matrix? D distance matrix. So basically it's just a 0 and 1 matrix, yeah, where it is 1, yeah. So maybe I'll just write it here. So we have here Aij. This is equal to 1, yeah, when Pi so the distance from Pi, to Pj is inside the distance set, yeah, and it is 0 when it is not, yeah. Yeah. Okay, so that's the distance matrix, yeah. And of course, when the D is equal to 1, yeah, a set of 1, this is just the adjacency matrix, yeah. Okay. All right. So we have this distance matrix, yeah, D distance matrix, yeah, of G. And then we also have the H as the distance magic labeling with magic constant. Yeah. Okay. So now we multiply A, yeah, this distance matrix with the labels, yeah, the labels of the magic labeling, yeah, so of the D magic labeling, yeah. So what will happen here? Yeah, so this is an n by n matrix. This is factor, yeah, n by 1. Of course, the result should be n by 1, yeah. So if we multiply this, what do you think will happen? Yeah, it's already written here, yeah. So this is equal to the magic constants times U. So basically the result will be just k, yeah, the factor k. Why is that? Because when we do this, yeah, when we multiply, we basically count the number of vertices inside the D neighborhood, right? Yeah, and then if we multiply with here, with the label, yeah, then we will get the magic constant, yeah, because we add, yeah, we add only labels of vertices inside the distance set, right? Yeah, of a particular set. Yeah, so this is going to be equal to k times the factor G. Okay. All right. So now say that this graph, yeah, has a neighborhood fractional dominating function, yeah, where it is the minimum one. This is the fractional dominating function with the minimum number, with the minimum sum of this, yeah. So this the sum is equal to the minimum number, yeah. Okay, so now if we multiply y with this one, yeah, this is the map of the fractional dominating function, yeah. So automatically from the definition, yeah, we have that if we sum, yeah, all the map of the function, yeah, map of the G function, where the sum is over all the vertices of distance in D, yeah, it will be greater than 1, yeah, greater or equal than 1. So what we do here is the same, right? Only we do it for every vertices, yeah, because we multiply with the distance matrix, yeah, and in this case it will be greater or equal than 1, yeah. Okay, so AY is greater or equal than 1. So now if we multiply this one, yeah, the transpose of this, yeah, with the AY, yeah, so it will be greater than the sum of all the labels, yeah, which is what, 1 up to n, right? Yeah, if we multiply the labels, yeah, the labels with this vertex here, which is greater than 1, right? So it will be greater than the sum of all the labels there. Yeah. Okay. So we do a simple what is that? Calculation, yeah, by using the properties of transpose matrix, yeah. So here, yeah, we can move the transpose. Yeah, you can follow this one. You open the transpose, yeah, and then here you have Y transpose. A transpose A is equal to AX. Why is that? Because A is a symmetric matrix. Yeah, this is just the distance matrix. Of course, it is symmetric. Then the transpose will be the same with A itself, right? So here we have already counted that AX is equal to K times U. Yeah, so I put it here. Yeah, and what is this? This is just K times, because here what we consider here is the fractional dominating function with the minimum, yeah, the minimum sum, right? So basically what we do here, we just count this sum, right? Yeah, so the K we can take out, right? But Y transpose times U here is just adding all the sum of GVI, right? And then we can get this one, yeah. Okay. Right, so if we move around, yeah, so here this one is greater than this one, sorry, this part here is greater than this, right? And this actually equal to this, yeah. So now we can get the lower bound for K, yeah, just, yeah, move the around, divide with this one, yeah. So this is n plus like n times n plus 1 over 2, yeah. We divide with this one, right? We get the lower bound for K. Yeah, so now we can prove, yeah, from here we can show that the magic constant is at least this number, yeah, which was already mentioned in the theorem. So now what to do next is just to show that K is also less or equal than this number, yeah. Okay, so this can be shown here, yeah. So basically we define a fractional dominating function where the map is just the label, yeah, the label of the magic labeling, yeah, the labels divided by the magic constant, yeah. So if you add them all, it will be, of course, greater or equal than 1, right? If we add like for all the matrices in D, right? So here we just have to count this, yes. Of course, the what is that? The minimum number, the minimum. This is the minimum sum of any fractional dominating function, and we choose one of them. Yeah. Of course, the minimum one should be less than this one. Yeah, because this one we don't know whether that will be minimum or not. Yeah. So this one should be less than this, yeah, the sum of this. And if we count, yeah, it will be something like this, which means we add all of the labels, yeah, and it's going to be n times n plus 1 over 2K. Yeah, so we get now the upper bound. Sorry, if we move K here, yeah, we get the upper bound for K. Yeah, so we get the upper bound for K before we have the lower bound for K. Yeah. Okay, sorry. This one. Yeah. So altogether we get that K. Sorry. Wrong button to press. Okay. This one, yeah. So from here we get that K is equal to this one. Yeah. As was already written in the theorem here. I just will show you the theorem again. Yeah. So the magic constant is unique with value, with this value. Yeah. So again, the tools for proving this is mainly the distance matrix of the graph. Yeah. Okay. So it is unique. So if we go back to our question, this one, yeah, is the D-magic constant of G unique? The answer is yes. Yeah. Now, what about the second question? Yeah, because okay, we already enlarged the distance set. Now, is it possible to label all graphs? Yeah. Okay, unfortunately, we don't have a positive answer for this. Yeah. So here again, I want to show you how we use the spectrum. Yeah. So the eigenvalues, yeah, of a graph, of an adjacency matrix of graph to show that distance magic graphs for a particular graph do not exist. Distance magic labeling. Sorry. Okay, so say we have a distance magic graph with this matrices, yeah, and of course because this is distance magic, we have the distance magic label, yeah. Okay, so now we have the weights, yeah, of each vertex, which is the sum of what? This is distance magic labeling, yeah. So this is just the distance one, yeah. So we don't consider the general case, yeah, where the distance is t. This is only distance one, but a similar argument can also be used for this further distance, yeah, distance. Okay, so now we count, yeah, we sum the weight, yeah. So basically, what we do is we just add all the vertices, all the labels of vertices adjacent to a vertex, yeah, and of course this will be k, yeah, for each of the vertices or the vertex. And we can rewrite this in terms of matrix multiplication, yeah. So this is the adjacency matrix times L. What is L? L is just the labels, right? If we times the matrix with the L, yeah, it will be again what we have before, yeah, K, yeah, because if we multiply this, yeah, for one row, it means we see like all the neighbors of the vertex, right? Yeah, in one row, we multiply with the labels. Of course, we only add the labels of the adjacent vertices, right? Yeah, so it's supposed to be equal to K, yeah. So again, we have this equation, yeah, just like before, but before we use d distance matrix, yeah. Here we just use a distance matrix. Okay, now if the graph is regular, yeah, if the graph is regular, yeah, we can have that if we use another factor here, yeah, not this factor, yeah, this is just the labels, right? But if we change with another factor, which is k over r, all k over r, yeah, because this is regular, yeah, if we multiply with a, it will also result with the same factor, right? Yeah, yeah. Okay, so because we just add k over r k times, right? Okay, so yeah, just to remind you of linear algebra, elementary linear algebra, yeah. So all of these are what is this? These are two eigenvector, right? So if we minus, yeah, the L and L minus one, it will be also an eigenvector, yeah. Here we have that A times L, yeah, we have this one, L minus one, which means AL times AL minus one, they have the same multiplicator, which is K, so it will be 0, yeah. So in this case, we have 0 is an eigenvector of the graph, yeah. 0 is not an eigenvector, an eigenvalue of the graph, yeah. 0 is an eigenvalue of the graph, so it is in the spectrum of the graph G, yeah. Okay, So this is a result by Martin Anhocher, Sylvia Chichas, and I think the name is Itok Petrin. Yeah. Is it? Iftok. Okay. In 2016. Yeah. So what we have here, if we have a regular graph, which is distance magic, then 0 is an eigenvalue of that graph, right? Okay. So now we can use this for a particular regular graph, which is the strongly regular graphs. Yeah. So here, I just want to remind you what is the strongly regular graph of parameters R, A, and C. Yeah. So the R is the regularity, right? And then if we take every adjacent vertices, it will have common neighbors, A of them. Yeah. And non-adjacent vertices will have also common neighbors, C of them. Yeah. So that's the definition of strongly regular graphs with parameter R, A, and C. Yeah. Okay. And it is well known. Yeah. It is already, this is a well-known result in strongly regular graphs, that if we have strongly regular graphs where 0 is an eigenvalue of that strongly regular graph, then the only possibility is for the graph to be regular complete multipartite. Yeah. So that's the only possibility for strongly regular graph with 0 as an eigenvalue. Yeah. Yeah, you can, I think you can try to find in the literature. Yeah, this is in algebraic graph theory books, I think. Okay. But yeah, it was also been proved. Yeah, I think I've shown you 2 days ago. Yeah, for regular complete multipartite graphs that has distance magic labeling. Yeah, is only this. Yeah, so they exist when n is even or both. Yeah, so n is what? N is the number of vertices inside partition, right? And P is the number of partitions. Yeah, so we can have distance magic labeling for this graph only when n is even and both n and P are on. Yeah, so this is, so if we combine these two, yeah, then this is what we have. Yeah, so the strongly regular graph, yeah, on n vertices is distance magic if and only if they are this complete multipartite graphs, yeah, with some conditions for the n and the p. Yeah. Okay. So this is for distance magic. Yeah. So distance magic means we consider d equal to 1. Yeah. But for strongly regular graphs, yeah, so all strongly regular graphs actually has diameter 2. Diameter at most 2, yeah. So the diameter of strongly regular graph, yeah, is almost. Yeah. So if we consider strongly regular graphs, yeah, the only possibilities for the D, yeah. So of course the D, so the D here should be, should be subset of 0, 1, and 2, right? Because the diameter is at most 2. Yeah. So the only possibilities for D is 1, yeah, or 0, right? Or maybe we can have D is 0, 1, yeah, D is 1, 2, yeah. What else? 0, 2, yeah, D 0, 2. Or we can have also D is equal to all of them, yeah, 0, 1, 2. Have I covered all of the possibilities? Yeah. Okay. Only 2. Okay. Yeah, that's correct. Only 2. Yeah, only 2 is here. Okay, 0, 1, 0, 2, 1, 2. Yeah, I think everything is here, right? Oh, yeah, 2. Sorry. All right. Okay, so I have all of them, yeah. And actually we can do similar things, yeah. We consider the, now not the adjacency matrix, but the D distance matrix, yeah. And we can show, yeah, similar tools that these are the only distance magic graph for strongly regular graph, yeah. So, Martin, Anholzer, and friends here, they prove for 0, 1, yeah, for 0, 1, and the rest we did in 2020 with my PhD student Paltuan Anulis, yeah. He was an MS student at that time. Okay, so here, so if we have strongly regular graph, yeah, and G will be D magic if only if this one, yeah, for D1 and 0, 2, yeah, only the complete multipartite graphs, and for 0, 1, and 2, it's only the KN, complete graph KN, yeah. So of course this is, so we don't really see this one here, yeah, because this is obvious, yeah, this one, right, yeah. So outside of this, yeah. So of course we can add also that one in here, yeah. So only this set of graphs actually, yeah, complete multipartites and complete graphs, yeah. Yeah. Oh, okay, yeah, sorry, this one is a mistake. Okay, so this is supposed to be 0 and 1, yeah, that's correct. Thank you. Yeah, so I will correct this. Yeah, this is supposed to be only 0 and 1. Okay, so just delete this one, yeah. So only 0 and 1, which is all the possible distances, right? Okay, so what I said before is we only for strongly regular graphs here, they are D magic if and only if they are complete multipartite graphs with several conditions and also complete graphs, yeah, when we add everything, yeah. But of course there are many, yeah, there are many strongly regular graphs, yeah. You can try to find out there are a lot of strongly regular graphs outside of this, yeah. So all of those graphs, yeah, all strongly regular graphs which are not complete multipartite, which are not complete graphs, we cannot label them D magically for any D. Yeah, it is not possible. Yeah. So the second question that I asked before, the answer is negative. Yeah, because we can find so many strongly regular graphs that cannot be labeled with any D. Yeah. Okay. All right. So what's next? Yeah. So what we did after that is we try to find the labeling for graphs which is distance regular. Yeah. So not strongly regular. Yeah. Strongly regular is also distance regular, but with small diameter. Yeah. But now we can have a larger diameter. Yeah. So the obvious example, yeah, is for hypercubes. Yeah. And actually, it is not that easy also for hypercube. Yeah. So here, I hope you still remember what a hypercube is. Yeah. So hypercube on n vertices, we usually use this notation. Yeah. So the vertices, yeah, there is a lot of way to define a hypercube. This is one of the way. So we basically consider the vertices as binary n factor, right? And then they will be adjacent if the factors differ only in one coordinate. Yeah, so this is one way to define the hypercube, yeah, which we use in our proofs. Okay, and then this is a result, yeah, from Gregor and Kovar, and I don't know how to pronounce Sylvia last name. Jihaj, okay. Jihaj, Dalibor, Francek, Elliot, Prof, Christopher Radidan. They prove that, so this is just distance 1, yeah, distance magic. Hypercube is distance magic if and only if the n is congruent to 2 modulo 4. Yeah, this is what they prove. So Gregor and Kovar provided the construction for n congruent to 0 modulo 4, and the others prove the non-existence, yeah, for the rest of the n. Okay. Now, of course, because we already enlarged, yeah, the distance under considerations. What about other d's? Yeah, this is only this distance d equal to 1. So our question is, what about other? Yeah. So as I mentioned before, hypercube is a distance regular graph. So this is the definition of distance regular graph with the notation that I will use later on. Yeah. So it is until 10:30. Okay. All right. Okay. Okay, so maybe I will go a bit fast. Yeah, so I will give all my slides to both Christoph and also Dr. Safras. Yeah, so hopefully they will distribute the slides. Yes, maybe I will skip several parts, but if you have questions, you can ask to me later on. Yeah. Okay. Okay, so this is the definition of a distance regular graph. So basically, we have an array, yeah, of distances. Yeah. So this is counting the number of neighbors in particular distance. Yeah. So here GIU, what is this? This is the set of vertices at distance I from U. Yeah. So now we want to have exactly CJ neighbors of U inside this one. Yeah. So basically of distance J minus 1. Yeah. So CJ neighbors in distance J minus 1. Yeah. And the other way around. Yeah. So from in J plus 1. Yeah. We want to have BJ neighbor. Yeah. Okay. So, and if we collect all the integers here, we can get what we call intersection array, yeah, of a distance regular graph. Okay, so from that we get what the 3-diagonal matrix of a distance regular graph. Yeah, so basically here what we have, yeah, so this is the intersection array. Yeah, and we put the R B1 until BD minus 1 here, right? Yeah. And the 1, C2, and CD in the, I don't know what. So this is next to the diagonal, yeah, in the upper part of the matrix, yeah. And we count the degree, yeah, the degree of the graph minus the sum of all this value, yeah, BI plus CI, right? And we put the value in here. Yeah, so this is what we call the 3-diagonal matrix, and this is a very common matrix to identify distance regular graph. Okay. Okay, so here we have 2 factors, yeah, connected to the 3-diagonal matrix. Yeah. So basically here we can add. So here we have a labeling of vertices, yeah, a labeling of vertices which we call L. So it is not yet the distance magic labeling, yeah. So this is just labeling of vertices L, and then if we multiply, so if we add, yeah, all the vertices inside GI, yeah, for that labeling, yeah, we will give the name SI here. Yeah. Okay. Yeah. So we will have that if we count 0, yeah. So if it is just 0, yeah. What is this? it means that we consider G0. So what is G0? G0 is just the set of vertices at distance 0 from you, which means itself, yeah, which means itself. So we have S0x is equal to the labelings, yeah. So now we have this vector, right? And we also have a vector K, yeah, where the elements of the vector is all the cardinalities of the GI. Yeah, so this is the second factor. The first factor is just we put like all the sum here, yeah, inside a factor, and here we count all the cardinality of GI inside one factor. Yeah, okay, so we call that factor K. Yeah, and if we do some calculation, yeah, based on the properties, yeah, of the tridiagonal matrix, yeah, we will find out that if we multiply the tridiagonal matrix with this vector, it will be this value, yeah. And if L is the distance magic labeling, yeah, if L is distance magic labeling, yeah, with magic constant K accent, if we multiply with B, it will be just K accent. So this is the magic constant, yeah, the unique magic constant times this vector, right? And if it is closed distance magic, it will fulfill this equation. Yeah. Okay. Right. Okay. So now we consider a spatial distance regular graph, which we call antipodal double cover. Yeah. So what is this? This means that GD. So this D is the diameter. Remember? Yeah. So for every X, for every vertex, yeah, there exactly one other vertex, yeah, with distance equal to the diameter. Yeah, so this is the meaning of this, yeah, right? Because GD means like the set of vertices with distance equal to D. Yeah, so you can see that hypercube is one of an antipodal double cover graph, right? Yeah, because for each vertex in a hypercube, we only have one other vertex at distance the diameter. Yeah, and we call that vertex the antipole. Yeah. Okay, so I think I will skip the reasoning. Yeah, so basically we use the multiplication of matrices with vectors that we have before. Yeah. What we have here, that, yeah, the result from here, yeah, basically this equation says that if we have a distance regular graph of diameter D, which is antipodal double cover like the hypercube, yeah, if it is distance magic or close distance magic, yeah, then automatically, yeah, the same labeling will give us this distance, yeah. They also will be magic with this distance, yeah. So for any J, yeah, for all J, yeah. So 1 and diameter -1, yeah, 2 and diameter -2, and so on, yeah. So if it is distance magic and close distance magic, automatically it will also be this magic, yeah. Okay. Okay, so if we put more restriction, yeah, so maybe you ask, why do you put, like, you start with distance regular and then antipodal double cover, right? And then now you want to be bipartite because you want to narrow our search into hypercube, right? So we put in like all the properties of hypercube, yeah. So now the bipartite one, right? Okay, so now we have, if G is a bipartite distance regular graph with antipodal double cover, diameter D, then if G has distance magic labeling, then the diameter should be this. Yeah. So this is just by looking into like switching of multiplication of matrix and a vector. and the S aspect factor, right? Okay, so here, if it has distance magic labeling, then the D should be 2 modulo 4. So this is basically a more general result than the result by Jihaz, Proncek, Prof, and Raridan that I have mentioned before. Yeah, they have proved that when n is not equal to 2 modulo 4, then the hypercube is not distance magic. Yeah, so this is an alternative proof of what they have proved in 2016. Yeah, using completely different. Okay, so now that's the negative result. Yeah, what about the positive one? So we consider n only 2 modulo 4, right, here, because remember here, to have distance magic labeling, the D has to be 2 modulo 4. Yeah, for hypercube, the D is the n, right? Yeah, the diameter is the n. Yeah, so here for n 2 modulo 4, yeah, we have this result. Yeah, it is if G admits distance magic labeling, yeah, then it is also D magic or alpha min D. Yeah, so this is for any D. Yeah, so if it is distance magic, then it is either D magic or D anti-magic. Yeah, so one of them should occur, right? And if it is bipartite, then it is D magic for all non-empty sets of this. Yeah, if it is bipartite, which hypercube is, right? Okay, so this is the main theorem that we prove that for 2 modulo 4, we can have D magic labeling for all the distance set which looks like this. Yeah, so this one is from here, yeah, 1, 3, 5, right? And we have I, yeah, this is the index, right? So basically this is just what we have before. Yeah, so remember, this is the one. Yeah, we have this one. Yeah, J, D minus J. Yeah. And here we have, so this one is from here. Yeah, so any non-empty set for odd distances. Yeah, so any non-empty set of what is that? Odd distances, and we can also union with the distances I and minus I. Yeah, for any index of I. Okay, so that's what we can construct. Yeah, the labeling that we can construct for all of this D. Yeah, for any form of, for any D in this form. Yeah, we can construct the label, right? But the question is now whether this is already all of them. Yeah, so have we covered all the distance set? Yeah, for the hypercube to be D magic. Yeah, so this is our question. Yeah, are these the only Ds? Yeah, probably not. Probably yes. I don't know. We still don't know what the answer, but we couldn't find anything else. Yeah, so this is what we can find. Probably, yeah, you or other people can find, yeah, other set that also will make hypercube D magic. Yeah, so this is for 2 modulo 4. Yeah, solid 1030. Okay, so what about for 2 modulo, not 2 modulo 4? Yeah, for 1 modulo 4, yeah, we found that it is close distance magic if and only if n is 1 modulo 4. Yeah, this is again we use matrix reasoning. Yeah, and again the question is what about other D's? Yeah, and then we can find these other D's. Yeah, so it should look like this. Yeah, to I plus 1, and then J minus n minus J. J and minus J. Yeah, so this is for n 1 modulo 4. And our question is the same, yeah. Have we covered all? Yeah, all possible D. Yeah. We can also find that for all n, yeah, not just one modulo 4 and two modulo 4, but for all n, it is also j and minus j magic, yeah. And for 1, 2, 3 modulo 4, yeah, this is similar techniques, yeah, that we use. It is 2n magic labeling, yeah. And this is the one negative result, yeah. For 0, 1 modulo 4, there is no 0, 2 magic labeling. Yeah, there is no 0. Yeah, so our conjecture is for 0, 2, yeah, it's only for Q2. Yeah, only exists for Q2. But yeah, we don't know for sure. Yeah. But again, for hypercubes and distance regular graph, we have question to find all the D's, yeah, for hypercube to be D magic. Yeah. And also when we have the diameter is greater than 3, so not strongly regular, yeah. So for strongly regular graph, we already proved that there are some strongly regular graph which are not D magic, right? A lot of them, right? But now, what if we extend the diameter? Yeah, if we consider larger diameter and ask the same question as before, is it true or not? Yeah. So we still don't know the answer for these two questions. Okay, thank you.